everybody. My name's Blake Griffith. I'm going to talk to you guys about conda. If you guys don't know what that is, I'll explain it. I'm on GitHub as Calix and Twitter as Calix with the Bowser. Yeah, I don't work for Continuum Analytics, who are the people that make conda. I am available for contract work though. So in this talk, I'm going to talk about conda and how it compares to the normal Python package manager, pip, or also known as pip installs packages. That's what it's an acronym for. How conda compares to wheel, which is like a pip plugin, and how conda is also kind of like virtualet. Then I'm going to talk about building conda packages and how those packages are distributed. So I'm going to get a few terms straight because a lot of people, there are several words that sound similar when we talk about conda. The first one is conda itself. It's an open source, language agnostic, cross-platform package manager. So language agnostic, which means you can install not just Python packages, but R packages for C programs or other Scala libraries or Perl. It's cross-platform. I only use it on Linux, but most of the Anaconda installations are on Windows, and it makes, and we're good, Leo. Is it? Good. Most conda installations are on Windows because it makes installing Python packages on Windows a lot easier than it was before with pip. Mini conda is what you actually download to install conda. And anaconda, like the snake, is a snake. Also, it's a bundle of software that includes a bunch of packages. So it comes with conda, the package installer. It also comes with like NumPy and SciPy and a bunch of other packages that you might use. And Continuum Analytics is the company that created conda, and it's also the people that host the package repositories for conda packages. They also create a bunch of conda packages. So I'm going to compare conda to pip a little bit. But before we do that, I kind of have to explain a little bit how pip works so we understand how conda is different from it. So whenever you pip install pandas, your computer goes to PyPI, the Python package index, and it downloads pandas as a source code that actually, whenever you open up the pandas repository, like everything's there. It's not like an executable binary or anything. It downloads that, it inspects the setup.py in the pandas project, and looks at what the requirements are. And then your computer sees these requirements, and it goes and downloads them from PyPI, and it does the same thing to those packages. It downloads them and inspects the setup requirements, and so on until all those requirements are satisfied. So if two requirements have the same dependency, it gets it once, and then if it sees another one, the same dependency again, it doesn't get it again. But if two requirements depend on different versions or conflicting versions, it just chooses the first one. And it won't tell you that two packages have conflicting dependencies. And then once you have all these requirements on your machine, it runs setup.py install on all of them and puts it in the right place. And so building these packages can also be take a lot of time if they are C extensions, like if you try to pip install NumPy. Has anyone ever done that before? Right. So depending on what platform you do it on, it might or might not work. If you do it on Windows, you will probably need whatever Visual Studio. If you do it on Linux, you might need GCC. unless you have wheel installed. I'll talk about wheel in a second, but I'm assuming you don't have, or I'm assuming we're not using wheel yet. I'll talk about wheel in a minute. Whenever you conda install something a little bit different happens. So if I were to conda install AstroPi, conda is aware of the metadata for this package separately from the package itself. So it goes to continuous repositories and says, before it downloads AstroPi itself, it says, what are AstroPi's requirements? Because there is like metadata information on the repositories. And then it looks up its dependencies from there and downloads the metadata for all those things. It brings the metadata for all the requirements to your machine without actually downloading all of the packages. It just downloads the metadata. It determines if the requirements are satisfiable, if it checks to see if there are conflicting versions, and if everything's good, it goes and downloads the code. So it's going to download the pre-built packages now. So it's not going to download the source code if it can avoid it. Conda is going to go and get a compiled version of NumPy and for AstroPi, and then install it in your machine. So you don't actually need the compile time dependencies. So you don't need the C compiler, and you don't have to wait around for things to compile. Also, if you conda install things with NumPy, you're going to get NumPy linked to the MKL, which is a little bit harder to do if you're pip installing things. MKL is like a standard math kernel library. It makes NumPy faster. I didn't show you this, so so this is what it looks like if I were to conda install pandas. You can see that it fetches the metadata and then installs the specifications. And I actually already had these packages cached, so it didn't even install them. I mean, it didn't download them, then it installed them into my conda environment. So what's the difference between pip and conda at like a high level? If conda doesn't have a need for build time dependencies, what's the second thing? There's no build time because the package is already built. So you download need dependencies that you would need at build time, like you would for pip, like a Fortran compiler or something. It's language agnostic, which is if I were to conda install NumPy, I can get it linked to the MKL because it's conda's language agnostic. So it's actually installing a C library, the math kernel library, into my machine, not just Python programs. And it has better dependency resolution. It'll let you know about requirement conflicts. So what about wheels? Does anybody know what wheels are? Cool. So wheels are pre-built Python packages. So they're kind of like conda packages in a few ways. Like you don't need build time dependencies, and you can just download them and install them without a build step. So they're kind of nice, but they have a few problems. They've always been broken on Linux, so you can't. PyPI doesn't accept wheels for Linux, and there are a few reasons for that, which I'll explain in a second. But also, wheels are not designed to install non-Python dependencies. And so if you have a Python package, or if you have a wheel that you want to install and it has an external dependency that's not a Python package, wheel doesn't handle that very well. There are some things it can do, but it's not designed to handle that. So why don't wheels work on Linux? You might not be on Linux, so you might not care, but it's kind of illuminates how conda works a little bit. So if I were to compile a wheel on Linux and try to give it to someone else, it might not work because the the binary code that's generated depends on some of the things that I compile the wheel against. So if I compile NumPy on my machine, and it depends on a C library called glibc, what that binary code will look like. And if somebody who I give this NumPy binary to has an older version of glibc, it's not forward compatible. So like if I compiled NumPy with a newer version of glibc, it might not work. But if I had an older version of glibc than them, the people that make glibc work really hard to keep things backwards compatible, so that would work. And also, whenever I compile things in a Linux environment, there are like other external dependencies that might not be captured in the wheel, things that aren't Python. And so, whenever the wheel specification was made, this stuff was not part of it. And on Windows and macOS, you have a much more homogeneous platform, and you kind of know what things are going to be there. So it's easier to compile binaries for those platforms that you know will work on every Windows machine. And that's not true for Linux necessarily. But just as of last month, there's a new PEP for fixing part of this problem. So if you look at this line that is wrapped, unfortunately, I can explain kind of how the proposal for fixing this. So this is what the wheel file name looks like. Python is for the datautil package. And the first part is the package name. The next part is the package version. And then the next part is the Python version. This is the API tag, the application binary interface. Don't worry about that. This is the platform tag. So the way that Wheels knows what operating system you're on. Whenever you try to pip install something, it will go to IPI and say like, I want the Windows wheel because I'm on Windows. But if it works for everything, it'll get the any wheel. If you're trying to pip install a wheel that works on any distribution. Yeah. So the PEP proposes to add a mini Linux 1 platform tag. There was already a Linux platform tag, but for the reasons that I already explained, IPI wasn't accepting those because they weren't easily portable between Linux installations. So, but what this mini Linux 1 platform tag says is like it's a promise that this wheel is compiled in such a way that it can be shared across multiple Linux installations. And so this PEP proposes a way to make wheels that can be shared across multiple Linux installations. And so the way that it proposes to do that is by doing basically what conda does. Whenever we build conda packages for Linux, or whenever Continuum builds them on Linux, it selects a subset of like the Linux user space, which is a bunch of C libraries. You don't have to read all this or know what those are. You just have to know like almost every Python installation on a Linux desktop or a Linux server is going to have all these things, and they're probably going to be newer than a certain version. So the PEP says this mini Linux 1 platform tag is a promise that this wheel was compiled on a machine that has libraries that are like old enough so that like everything that's newer will be compatible with them, and everything is going to have all these libraries, so it should work whenever you put this wheel on a bunch of different machines. So we can revisit the question of why wheels don't work on Linux. The core shared libraries like glibc and all those ones that I just listed, this kind of fixes that problem. The wheel still doesn't have a way of capturing external dependencies. So if I were to try to install like Pi0 MQ, that depends on the libc or MQ library, which doesn't usually come with a Linux installation or Windows or macOS installation for that matter. I actually have to install it with my system package manager. So there isn't a way of capturing non-Python external dependencies in wheels yet. You can kind of bundle them into the wheel, but it's not supported very well, and it's kind of a dirty hack. But the PEP actually proposes it gives you some tooling to bundle these dependencies with the wheel. But bundling the dependencies with the wheel, instead of declaring it as like having these dependencies and letting your operating system get those, has a few problems. Well, it's easy. So what the PEP says to do is if I wanted to install pi0mq, I would just stick lib0mq in the library, in the wheel, which is how a lot of things like this is bundling or like containerization. It's kind of like a popular thing now, but it's easy to do. But and also it doesn't the wheel doesn't have to worry about its dependencies updating because it's included its dependencies are included in itself. So something else isn't going to update them. So it isn't going to break. But there are some problems where like if you have two different wheels and they have the same dependency and they have the same version bundled with them or different versions bundled with them, and they try to talk to each other somehow, that can cause problems. So because they have the same dependency but different versions, and there can be issues with there. It can also be illegal in some ways so whenever you compile something, you can include its dependencies by statically compiling it, which just means like I'm creating this executable program and I'm going to stick everything that it depends on in there with it. Or you can dynamically link its dependencies, which just says, I made this thing and its dependencies are on the machine somewhere, and here's how you would go find them, but they're not actually included in this executable piece of code. And if something is licensed with the LGPL open source license, if you want to distribute proprietary software, you can't statically link LGPL code, but you can dynamically link LGPL code. Or someone's going to see you. And then there is a larger problem. So if we remember some horrible security thing that happened, like a hard bleed, for example, if I have some Python software that depends on OpenSSL, like pip does, and I statically bundle its dependencies with it, then I'll have multiple Python wheels that have an older version of OpenSSL in them. So whenever I need to update OpenSSL on my machine, I can update the one that my operating system has. But then all of these wheels have older versions of it built into them. And I have to count on the package maintainers to update those things quickly, which I don't know that they'll do. I can't really just count on me doing it myself and it being fixed everywhere. So the bundling proposed in this PEP, the way that it wants to handle external dependencies, probably isn't going to fix everything with wheels. Well, it's not. So the way conda manages dependencies is kind of like how your operating system manages them. It has a /lib directory, and packages that need those things they link to it. So this is a dependency graph for Python on my machine, which I generated with that code, and you can see like Python itself depends on these other packages, which all depend on other things. And you can see like some of the packages that Python itself depends on actually share dependencies, like they share dpackage, which if these things were bundled, they would all have their own copy of dpackage, and they would all be updated separately. So if there was a bug in dpackage, all I would have to do is update dpackage, and everything else would be updated. So I'm going to talk about virtualing now, conda also includes environments, which are basically, conda's environments are basically a superset of virtualing environments. But virtualing doesn't actually do much. You just create a virtual environment, and there's no way for you to share that virtual environment. So you have to use pip to like capture all the packages that are installed with pip and put it in a file and install them later. You can pass around this virtual directory, but that's a pretty big thing. It's not something you would like want to check in to get and share with your project or anything like you would a requirements file. So conda environments are different from virtual environments because you can conda install things in them. And it also has a different spec for requirements that captures more information. It captures the things that are conda installed, the things that are pip installed, and their versions and the environment name. It's easy to make copies of these environments, and it's easy to share them. And part of the impetus for conda wasn't just to like solve some of these Python packaging problems, but also like reproducibility was important to the people that were making it. So they kind of wanted to create an environment system that was more easily reproducible than pip and virtualing. And so conda environments do that in a better way because they're not just capturing the Python version, the Python packages that are installed, they're capturing more things in your environment. And so another reason, so one reason I think you should use conda environments is not just because of that, but also like if you are working on an open source project and you want other people to use it, it's easier to get a development environment started with conda if you depend on things that are not just your Python libraries. So if I were to like git clone some project and but don't have all, and it's not pure Python dependencies, then you're going to miss stuff whenever you try to pip install a requirements file. And like you run a test or something to see if you have the package properly installed. It's just a much more straightforward way to get started on a open source project than pip install requirements.txt and then install these things with your system package manager. With conda, you can just create an environment and it's going to get things the right way, hopefully. Or hopefully it'll just do things better than the way pip did it. And a few more reasons to use conda is that you don't need administrative privileges to install it. It goes in a directory in your home directory, and it adds its bin directory to your path. And also, it's nice because since it is for managing not just Python packages, you can do things like, say, I want to use Python 3.6 in this environment. So like an alpha version of Python. So conda will, this line, conda create -n -yn Python 3.6. It'll create an environment called -yn, and then it'll download the version, Python version 3.6, and that'll be your Python interpreter. I always had to Google how to like make a virtualenv with whatever version of Python if you wanted them in different versions. It wasn't always obvious to me, and then you have to install those versions of Python with a different package manager, not that you usually have to like install them with your system package manager. But you can still use pip if you have conda environments. So you could just make a conda environment and pretend like it's a virtual environment if you wanted to. And it just makes things easier and faster because you don't have to wait for build time and you have to download extra build time dependencies. So I guess talk about why people should use conda and stuff a lot, but we actually need people to build conda packages. there are tons of examples of how to build conda packages at this GitHub repository. You just add a directory called conda recipe to your project, and it's going to have 3 files: a meta.yaml that tracks the metadata, the build.sh, which will probably just be something like python setup.py install, and then a run test file. So the conda packaging specification also includes a way for the package to test itself, which is what this run test.py file is. So I'll explain some of these files. Here's an example meta.yaml. It's pretty simple. There's just information about the package, like a summary, a description, its licensing information, the relative source to this file itself, and then its build time requirements, which are separate from its runtime requirements down here. And yeah, and then there's also test time requirements, which are usually different. Especially if you're developing, you might need you might have dependencies on like a testing library, like PyTest or something. This is the build.sh file for this conda package. It's really simple. It's just how to install the package. And then the example run test.py file. It's just how you run the tests for your project. You don't have to read code today. And then there's a service called anaconda.org. So you have a project, you built a package for it. What are you going to do with it? Anaconda.org is a tool for distributing conda packages. It's where all the conda packages you download with conda come from. You can point it at a GitHub repository and give it a GitHub. And whenever you push to the master branch, it will build your conda recipe and run the test there. So it serves as a continuous integration platform, and it'll test your repository against Linux, Windows, and Mac OS X. And you can also have private repositories where you can do things like this, but that costs money. It's also a service that's kind of like sort of like what GitHub is, since you can like pip install from the GitHub repository, something like that. But you can also conda install from anaconda.org, where you just do -c is like Blake's channel, and my package is whatever the name of the package is, and then the master branch. So I'm installing a pre-built binary that was built whenever I pushed the master. And then there's some built-in tools with conda for inspecting anaconda.org and seeing if your build passed, so you don't actually have to go to the website. Yeah, so I think that's it. Does anybody have any questions?
Sure. So if you want to, if you have a package that depends on something that's not in anaconda.org, what do you do?
So you ideally should, you can have a conda package that depends on packages that are in PyPI that can be tip installed. Although, yeah, you can do that, but you should just build a conda package for it. That way there's better coverage of everything.
So you can submit a conda package for packages that you don't maintain?
Yes. Yeah. You can. There's also a tool called conda skeleton, which just builds conda packages from Python projects. So you can say conda skeleton and then this PyPI URL, and it'll give you a conda recipe that will work 90% of the time. If they're doing something tricky, it might not.
We were talking about, you said that conda could install other things
Yeah, so a lot of people are using conda for R. I don't know too many R users, but whenever I heard that continuum, I knew that was happening. It is also tested every time you install something that is a Python project that depends on other things. Like if I conda install IPython with ND-convert, it's installing pandoc, which is like written in Haskell. If I install like I'm also installing C libraries whenever I conda install things. Yeah. Which pip can do.
Another question. Do you remember that you were talking about the legal article that ran about so many package managers?
Yeah.
What's your comment on that?
Oh yeah. I don't know. I guess that there are a lot of package managers because a lot of them don't work very well. So then people want to make a new one, and then we have another problem, which is that there's just too many package managers. Like conda, I actually was looking at that list, and there are two things that conda has that like none of the other ones have, which is that it's cross-platform. It's also cross-language. And that one had a few other requirements though, like there had 4 requirements, like be able to install source, which conda can't really do because it was built trying to answer problems that pip wasn't solving, and pip is a source package manager. But I think it's special.
So kind of dovetailing on that, I noticed that on the cross-platform stuff, you mentioned the spec of the conda package, and there was a build.sh in there.
Yeah.
Does that mean that all builds happen on Unix systems?
No, you can make a build.bat file too, which is pretty much the same thing as that. Yeah. So you usually have a build.sh and a build.bat, and then set up